All right, it's 9 o'clock. Good morning, everyone. I apologize first. My built-in camera of my laptop doesn't work since last week, so I just couldn't turn on my camera right now. I'm honored and happy to introduce Maggie Ellis Curry, our speaker for the Bureau Seminar Series today. Maggie is no stranger to the Bureau as she has been here twice. She's currently an assistant professor of tectonics, basins, and surface processes at the University of Houston. She got her master's degrees here at UT Austin with a frat group at the BEG, then worked for ExxonMobil in Houston before returning to grad school again for PhD. She got her PhD at the University of North Carolina, Chapel Hill in 2015. Then she returned to BG again for postdoc with the AGL group, then moved to Europe for her second postdoc at the University of Grenoble in France. Since this year, she has been with University of Houston this year. She works in the basins and mountains around the world, striving to understand feedbacks between tectonics, basin development, and surface processes in various tectonic settings. And I'll turn the stage to Maggie. Maggie, you can share your screens now. Thank
All
you.
right. Thank you, Lucy. Hi, everybody. I'm going to share the screen. Right. So thanks, everyone. Thanks again. And thanks for this invitation to present. Wish I could have come in person. It would have been fun to see all of you again, but the world is weird. So this is good, too. As Lucy said, I worked there at the BEG at 2 different times in my career with 2 different groups, which is actually fairly reflective of my varied background. I've worked in both academia and industry, and I've had different focuses in structure, basin analysis, geomorphology, and tectonics. And these different research focuses and experiences have made me really interested in how the different parts of a tectonic system interact. So what feedbacks exist between deformational, depositional, and surface processes. Make sure I got to get my laser pointer on. Oops. Laser pointer. So this systemic approach can be conceptualized by this illustration of source to sink systems. So tectonics, I've got the zoom window like kind of blocking my view here. Sorry, one second. See if I can move it down. Okay, so tectonics, they cause surface and rock uplift and basin subsidence. The surface processes will redistribute the mass, connecting these erosive landscapes to these depositional landscapes, moving material from the source to the sink. And then these, of course, are modulated by atmospheric and mantle processes. But today, I mean, there are several different tectonic settings represented here. And today I'm going to be talking about convergent systems and mountain landscapes, tell you about this work I've been doing in the Pyrenees. So truthfully, I'm really drawn to mountains and their landscapes like this one. And I want to understand the processes that shape them. They present a complicated problem because the landscape that we observe is part of this really dynamic system. And it's a result of these interactions and feedbacks between tectonics, climate, surface processes, lithology, human impact. All of these factors and more influence tectonically driven topography. And not only that, but they influence each other. So, the surface processes can actually influence the deformation, and then the deformation can affect the surface processes. So it's complicated, which makes unraveling these signals difficult, but it's also what makes mountains so compelling to research. So the question driving much of my research and what I will be addressing today is, how do landscapes, deposition, and deformation co-evolve in a developing orogen? And there are many ways to approach this question. And for my presentation today, I'm going to be addressing these 2 driving questions. First, how has the topography of the Pyrenees evolved through time? And second, how have rocks exhumed in space and time within that topographic framework? So I want to start by talking a little bit about mountain topography. Now, if you consider the life cycle of tectonically driven topography, there's this initial period of active deformation, rapid tectonic influx where the topography is growing and surface processes respond. Then perhaps a period of steady state when the tectonic influx and the surface processes are in equilibrium. But ultimately, that active deformation ceases and the surface processes begin to dominate and dismantle the mountain topography. So this is one somewhat theoretical model for the evolution of mountain topography, and there are others. There are also a lot of data describing the thermal evolution of orogens. There are geodynamic and geomorphic models that help our understanding of how orogens evolve. But the truth is there are very few studies that have actually documented topography over the lifetime of an orogen. But does that matter? I mean, who cares? Why do we need paleotopography? Well, as I mentioned at the beginning of this talk, these landscapes that we observe, this is the surface manifestation of all these competing forces. Topography is this key boundary condition in studies of tectonics, climate, geodynamics, and surface processes. So they're very important, but they tend to either be ignored in these types of models, or it's just assumed to be constant. The topography is just assumed to be constant through time. So I know no one wants to read a bunch of text on a slide here, but bear with me. These are just some quotes from a smattering of studies, all from very, respectable peer-reviewed journals. And they all say things like, topography is not addressed in any quantitative way. We use the present day surface topography throughout the model time period, so on and so forth. Acknowledgement that these things are highly sensitive to surface topography. And, I didn't even have to try very hard to find these quotes. These are only relating to the Pyrenees, actually. And finally, my favorite one, well, there are no published data that constrain the paleotopography of the Pyrenees. So, we just use the present day one all through the time. So when I was starting this project, it became clear to me that the first step towards really understanding these feedbacks in mountain systems and start interpreting the data in the most accurate way, we first need to constrain the topography. So that's what I'm going to do. But first, I'll give you some background on the Pyrenees. So the Pyrenees comprise a mountain range between France and Spain with peaks over 3,000 meters. So this is really high, rugged topography. The Pyrenees are an asymmetric double wedge orogen that formed due to the convergence between the Iberian and the European plates, beginning in the late Cretaceous and lasting till about the Miocene, roughly 25 million years ago. Prior to orogenesis, Pyrenean orogenesis, the boundary between Iberia and Europe was a rifted margin, and then the ensuing compression inverted these Mesozoic rift structures, which had a profound effect on the future geologic and structural evolution. The Pyrenees Mountains are flanked by two foreland basins, the Aquitaine foreland basin in the north, which makes up the retro foreland basin, and the Ebro-pro foreland basin in the south. These foreland basins contain a really complete record of deformation since the Cretaceous. And thanks to extensive research efforts, the structure and the stratigraphy of the Pyrenees and its foreland basins is really well constrained, which makes this a really nice area to study the feedbacks between the deformation, the deposition, and surface processes. Excuse me. So my approach towards investigating the paleotopography involves a method called flexural modeling. So I'd like to give you a crash course in that now. So the lithosphere has strength to it. And when it is subjected to a load, it warps downward in response. I like to give the analogy of this is sort of like if you or a pig were to stand on a diving board. In this case, the pig is the load, and you can see how the diving board is deflecting downward beneath the weight of the pig. Now, mountain building, well, it does just that. It builds a mountain, which creates a topographic load, and it causes the lithosphere to deflect downward beneath its weight. And it is this downward deflection of the lithosphere that facilitates formation of the foreland basins. And as such, the foreland basin stratigraphy contains a record of the flexure through time. This behavior of the lithosphere is governed by a fourth order partial differential equation, which I promise I'm not going to attempt to derive right now, but this is useful because it allows us to predict how the lithosphere will respond to different types of load scenarios. So if we know the topographic load and some physical parameters of the crust, we can predict the deflection. Now, this was really interesting to me for my purposes, because if we can use the topographic load to predict the deflection, it follows that the inverse is also true and that we can use the deflection to predict the topographic load. So the most influential parameters in these equations are the load and the rigidity, which is represented by effective elastic thickness, or TE. And these will influence the flexure in different and observable ways that are represented here. So the load shown up at the top, this will mostly affect the magnitude of the deflection, but it doesn't affect the wavelength. The rigidity, on the other hand, will affect both the magnitude and the wavelength of the deflection. So these somewhat schematic diagrams show how the flexure would vary when you change only the load versus the rigidity. And by looking at these, you can start to get an idea of how we can use observations of the foreland basin fill to make inferences about the flexural history and in turn the topographic history. And here I just circled TE, which is an important parameter, and I'm going to be talking more about later. And so just a reminder, that's a representation of the rigidity of the crust. Now, the real utility in modeling the flexure in this way is to be able to compare the results to data. And so the key is to have accurate and lots of data that can describe the deflection. And again, this is what makes the Pyrenees a really nice place to apply this. So for the first part of my modeling, I'm going to address this question: can the modern Pyrenean system be described with a flexural model? So in this scenario, we know the topography. This is just the modern orogenic topography. And we know the deflection, which is represented by the base of the foreland basin sequence. And that surface is shown here, along with some of the well bores that I used to constrain the surface. So the goal here is to determine the rigidity, or the elastic thickness, for each plate that can best model this data. So here are the results from this stage of modeling. So let me walk through, there's a lot on this slide. Let me walk through what I'm showing you here. So this is the results of the modeling with, on the vertical axis, you see the TE of the European plate. On the horizontal axis, the TE of the Iberian plate. So recall, the goal here was to determine the TE, the elastic thickness of each plate that can best reproduce the foreland basin that we observe. And the combination I found that minimizes the misfit, which is calculated as root mean square error, is right here. So this gives a value for 16 kilometers for the Iberian plate and 23 kilometers for the European plate, with a root mean square error of about 450 meters. And this map here, this is just showing the observed deflection, which is also shown by this surface here. Oh, sorry, no, this up top, the top one here is the predicted deflection. The bottom one is the observed one. And this surface shows those, the observed minus the modeled. So it's a representation of the goodness of fit. The dark colors here are areas where there's poor fit, and the contour lines here show that misfit, the observed minus the modeled. And this is in values of kilometers. So what you can see is that most of the foreland basins are being predicted within about 500 meters of their actual value. So it's a pretty good fit. And these areas of really high misfit tend to correspond to major structures that are influencing the shape of the basin. So for example, this really dark splotch right here in the Western Aquitaine Basin, this is where these Mesozoic extensional structures are having a really big effect on the geometry. So this is the Bay of Biscay basically out here. So to answer this question, can the modern Pyrenean system be described by a flexural model? These results indicate that yes, The majority of the foreland basin depths can be predicted to within 500 meters using a flexural model. So that allows me, now that I've established that, allows me to move on to the question I'm really interested in, which is how did the topography of the Pyrenees evolve? So these animations are showing how the topographic load and the basin will co-evolve. So as you increase the topographic load, you increase the deflection. So if I want to determine the topographic load through time, it means that I need to know the deflection through time. So a key point here, and what sets this study apart from other similar studies, is that we have this exceptional geologic record that has allowed me to reconstruct the foreland basin geometry at several time intervals. And I then use these reconstructed geometries as constraints in my model to determine that topographic load. So I mapped several stratigraphic surfaces in each foreland basin using wells, published and proprietary structural restorations and cross sections, paleogeographic maps and geophysical data. And I then used backstripping and restoration techniques to backstep the foreland basin geometry at each time interval. So what can we learn then about the topographic evolution? So in this instance, we do not know the topography, but thanks to those reconstructed foreland basins, we do know the deflection through time. So the way I designed this modeling is I start with the modern topography and those best fit TE results that I established in the previous step. Okay, and then I then vary these by factors I call tau and eta. So for example, I vary the topography by a factor called tau. So a tau factor of 0.5 means it's using topography equivalent to 50% as modern in the model. I'm going to show the results on a plot like this. This is going to be tau value on the vertical axis. So as you're increasing that tau value, you're increasing the topography. And then the horizontal axis is going to be that eta factor, so TE increasing from left to right. So I'm going to jump through the best fit results for each time interval, starting here with this Paleocene interval. So this plot's here on the plot, which is both at eta and a tau value of 0.6. So this means that in the Paleocene, the topography was 60% of modern. I'll jump to the mid-Eocene, the top of the Eocene, the Oligocene. And so what these points are showing is that from the Paleocene to the Oligocene was a period of topographic growth. And if I plot the present day scenario here, so just the one-to-one area, you can see that it also suggests a period of topographic decay from the Oligocene to the present. There's also a rigidity increase implied by these results. So just to show these results in a different way and really answer this question of how has the topography of the Pyrenees evolved, this plot shows the topographic relief through time. This is time on the x-axis and topographic relief on the y-axis. And these are the results based on that modeling, those results I just showed you. What these show is that the topographic load doubled from the Paleocene to the Oligocene. The most rapid growth was occurring during the Eocene. Also, modern topography was achieved by about the end of the Eocene. Since the end of convergence and the end of the Oligocene, there's been only really slow and limited decay to the present. And these results are consistent with the few other independent studies that have been done on the topography of the Pyrenees. So these results are cool, and they're helpful for a couple of reasons. For one, this is the first time to my knowledge that the topography of an orogen has been documented throughout its lifetime. So it helps us understand orogenic topography in a more general sense. But they also fill a gap in our knowledge of the Pyrenees, and they allow us to move forward in our understanding, for example, by providing constraints in models where in the past that has just been a free parameter. And so the second part of my talk is going to involve doing just that. I'm going to investigate how have the rocks exhumed in the Pyrenean origin in space and time within that topographic framework that I just established. So part of this long history of research of the Pyrenees that I mentioned includes a significant effort to collect thermochronology data from the origin. At this point, the community has amassed a pretty impressive data set. That is what these colorful dots are showing here. These include multiple thermochronometers, and it covers the majority of the origin. This large data set is powerful because it enables us to take an origin scale look at the trends and rates of rock cooling. So I'm going to use this large data set to investigate those trends using thermo-kinematic modeling. So I'm going to be talking about thermochronology data. I want to give just a quick background in that for those of us who might not remember. So thermochronology provides cooling ages for different minerals, and it is based on the temperature-dependent retention of radiogenic decay products. So here is a plot of some common thermochronometers and their temperature sensitivities. So now, in order to use this type of data to answer questions about Earth processes, we must tie those processes to changes in temperature. So for example, rock exhumation cools rocks down as they move upward through Earth's geotherm. So as an example, let's consider the apatite uranium, thorium, helium method, which is one of my personal favorites. And this is sensitive to temperatures around 75 degrees C. So this is a sort of a box schematic diagram showing rock exhumation. And these little gray circles, these are obviously rocks that I'm going to simulate. So as rocks containing apatite exhume from hot temperatures, they cool down. And once they pass through that 73-degree isotherm, that clock starts. So by reading that clock today, we can tell how long ago it passed through that isotherm. Now, by combining several thermochronometers, we can learn a lot about a rock's trajectory through the Earth. In this talk today, I'm going to be considering these 4 thermochronometers used in the Pyrenees. So as I've just discussed, the modern Pyrenees are mostly Cenozoic origin. The foreland basins contain a Cenozoic succession, but the tectonic history goes all the way back to the Paleozoic, when the area making up the core of the origin, was affected by the Variscan orogeny, which affected much of the European continent. It then underwent rifting in the Mesozoic, and it formed a hyperextended margin. And very shortly after Mesozoic extension, convergence between the Iberian and European plates commenced, which inverted those Mesozoic rift structures. Now, these 3 superimposed tectonic events result in really complex along strike structural variations. And I'm going to be exploring what those variations, how those variations are reflected in Pyrenean exhumation. My approach is going to use the thermokinematic modeling code P-cube. P-cube uses a finite element method to solve the heat transport equation in 3D, and then tracks the path and temperatures of rocks as they are advected upwards through a finite topography. So it can predict cooling ages for any thermochronometer. Furthermore, it incorporates the neighborhood algorithm, which allows for direct inversion of thermochronology data. So this model will search within the parameter space to find the results that best match the observed thermochron data. I'm going to focus on a large region of the Pyrenees right here in the center of the origin. And I utilize over 300 thermochronology samples, including apatite, uranium, thorium, helium, apatite fission track, zircon, uranium, thorium, helium, and zircon fission track. And collectively, these thermochronometers record rock cooling from about 300 degrees C. Here's my inversion setup, and let me walk you through this. So this plot shows time on that x-axis, and this is rock uplift rate on the y-axis. And these blue boxes show the time intervals within which I inverted for rock uplift rate. All right, and in the background, you can see this gray line here. This is the topographic evolution that I just finished telling you guys about. So this is a set parameter in the model that the rocks are advected through. Another thing to note here is that these gray boxes, for example, right here, is where I explicitly set the rock uplift rate. I didn't invert. So this is the post-orogenic period where you can see there's really slow rock uplift rate. I also inverted for valley fill. So there is a period of time in the Pyrenees, and I'll talk more about it in a little bit, where a lot of the foreland basins experienced aggradation. And so this is attempting to mimic that effect by aggrading and then eroding sediment. So just to summarize here, I'm inverting for rock uplift rate at several time periods, and then this valley fill. Okay, so first thing that I want to establish is what type of spatio-temporal model best fits the Pyrenees. So as sort of a base reference model, I use this uniform block uplift of the axial zone. And I then compare that to two different models. First, this structurally controlled exhumation, where these major thrusts and structures dictate the timing and rate of exhumation. This really also amounts to a north to south trend in exhumation. And then second is in a long strike trend and variation, where I allowed the rock uplift rate to vary along strike, as opposed to north to south, cross strike. And here are the results of those inversions represented as a misfit, which is a reduced chi-squared calculation. So the reference model has the worst fit of about 14. The structurally controlled exhumation also has a pretty low fit to the pretty high misfit to the data. And the best model is actually the long strike variation, which has by far the lowest misfit of about 5.5. So moving forward, this is the model that I'm going to be considering and talking about. So I want to look in more detail at these long strike trends. And these are box plots of the 4 thermochronometers utilized in the study. They're separated by zones from east to west. These colors all match throughout. You can see those zones here. And as you move from left to right across this stream, you're going to cooler temperature sensitivities, with zircon fission track being the highest temperature sensitivity, apatite, thorium, helium, the lowest. So again, these are the data. This is the actual thermochron cooling ages that I compiled. And here are the predicted ages based on the modeling. So you can see, I'm predicting these ages and this long strike trend pretty well. And an important observation here is that as you move to lower temperature thermochronometers, this east-west variation becomes a lot more pronounced. So just to show this another way, this plot is going to show rock uplift rate here on the vertical axis, and this is west to east distance along the horizontal axis. And what I'm going to do is I'm going to bounce through these curves that show how the rock uplift rate changed in space and in time, starting with the period from 50 to 40 MA, where you can see the Eastern Pyrenees were undergoing moderate rock uplift, the Western Pyrenees, almost none. Then you have 40 to 30 MA, which is a pretty similar trend, moderate to high rock uplift in the Eastern Pyrenees, very low in the Western Pyrenees, which abruptly switches from 30 to 20 MA, rapid uplift in the Western Pyrenees, very low in the Eastern Pyrenees. So I describe this as a westward propagating wave of deformation that swept from the east to the west. Now, because we constrained the topography, we can use these rock uplift rates to determine exhumation through time. So this plot shows time now on the x-axis going from about 56 to 0 MA. And then this is cumulative exhumation on the y-axis. These different colored lines represent the exhumation within these different zones. So these blue and green lines, which represent the Eastern Pyrenees, you can see they exhumed and accumulated their exhumation relatively quickly compared to the orange and yellow lines, which sort of lagged behind. This plot shows the same thing in just a different way, just to give you an idea of how these trends are changing through time. So here at 40 MA, you can see the Eastern Pyrenees have already experienced more exhumation. That becomes more pronounced at 30 MA. And then between 30 and 20 MA, the Western Pyrenees accumulate a lot more exhumation. And these gray boxes show post-orogenic exhumation. And you can see that is dominated also in the Western Pyrenees. So the way I would describe this is that the Eastern Pyrenees underwent the most Cenozoic exhumation, whereas the Western Pyrenees underwent the most late and post-orogenic exhumation. So there are two interesting points to consider coming out of this analysis. First is this really notable along strike trend. So if you look at the zircon fission track, all these ages cluster around 40 MA, whereas the apatite helium, which is sensitive to about 60 to 80 degrees C, have this really significant younging trend moving towards the west. Another point is that in the Western Pyrenees, we have these apatite helium cooling ages that are mid to late Miocene, marking a post-orogenic exhumation event that is seen only in the West. We see no evidence of that really in the East. So then, of course, the question is, why is this happening? What is causing this pattern? What I propose is that both of these observations, the along strike trend and the young cooling ages, these can be explained by considering along strike variations that are inherited from the previous tectonic phases and the post-orogenic surface processes. So first, let's consider this along strike trend. So these along strike variations can be tracked all the way back to the Variscan. These are two restored cross sections from the west, showing these red lines here. The Western Pyrenees at the top, Eastern Pyrenees at the bottom. Now it has been interpreted that prior to convergence, the Western Pyrenees comprise this really wide extensional zone, a broad region of transitional crust. Whereas in the Eastern Pyrenees, the rifting was more distributed with a much smaller zone of transitional crust, a less hyperextended margin. These rifting behaviors actually reflect the inherited Variscan crustal zonation. So if you look at this map here, which is showing the axial zone, this black line delineates rocks that belong to the Variscan hinterland to the north and east versus the Variscan foreland to the south and west. So in the west, these rocks were largely in the sort of undeformed, unmetamorphosed Variscan foreland rocks, whereas in the west, these Variscan hinterland rocks had a really strong foliation, they're more deformed, and this actually facilitated this more distributed rifting. Excuse me, let's get the water here. So this rifting scenario that you observe then influenced the modern Pyrenean thrust system with these more highly deformed imbricates and steepened thrust sheets in the east than the west. So to walk through this Variscan crustal zonation, which influenced this variable rheology, this affected the Mesozoic rifting by varying between concentrated versus really distributed extension in the west and the east. And then this in turn influenced the Pyrenean thrust. In particular, due to this pre-orogenic template, the onset of crustal thickening, of significant crustal thickening, began earlier in the east than the west. And I propose that this diachronous crustal thickening is the mechanism controlling that along strike trend. So you had this really rapid thickening of the crust occur much sooner in the east, causing more rapid exhumation earlier than the west. So that can get us part of the way there, but it doesn't explain these late Miocene cooling ages in the west. So I guess this is where I need to check my time. I think I'm okay. So we have these really young cooling ages in the west. Now, as a reminder, convergence in the Pyrenees ceased about 25, maybe 20 MA at the latest. There's no observed deformation in the axial zone since then. There's no obvious tectonic mechanism to explain these young cooling ages. And yet the Western Pyrenees has young cooling ages ranging from about 15 to 7 MA. So the question that remains here is what caused 2 to 3 kilometers of exhumation, about 15 to 7 MA, only in the Western Pyrenees? And this 2 to 3 kilometers comes from the fact that this is seen only in the apatite uranium, thorium, helium thermochronometer, which is sensitive to this range of temperatures, which depending on the geotherm makes for about 2 to 3 kilometers of exhumation. So what caused this only in the Western Pyrenees? Well, I propose that 3 synergistic circumstances drove this post-orogenic erosion. First, greater stream power due to base level fall. Second, isostatic rebound. And third, variable substrate erodibility. So let me walk through these to finish my talk here. But to do this, I need to start by telling you about the Ebro Basin. This is the southern foreland of the Pyrenees, and in the Eocene, the Ebro Basin used to drain to the north, to the Atlantic. But around 35 MA, the Ebro Basin closed and became endorheic. It then backfilled with several kilometers of conglomeratic material, mostly fed from the high Pyrenees. And then about 13 MA, the Ebro Basin connected to the Mediterranean. This caused a massive drop in base level and launched a powerful erosive wave that ultimately excavated the basin. Work done by Garcia Castellanos and Lara Sonia in 2015 calculated the volume of material that was excavated from the Ebro, and then calculated the isostatic rebound that would have occurred due to that excavation. And those results are shown here. This is the 200 and 100 meter contour, which you can see cutting across the Pyrenees with greater values in the west. So that gets us part of the way. We got base level fall. We have isostatic rebound. Excuse me. But there's another factor we need to consider here, which is the rock erodibility. Okay, so excuse me, I need to get just a little water. Okay. So we know there was this powerful erosive event in the late Miocene, and that the isostatic effect may have been greater in the west. But the final factor, as I said, is the lithology of the Pyrenean hinterland. So mapped here again is that boundary between the Variscan foreland and the Variscan hinterland. These white dots, these show the cooling ages, the apatite helium cooling ages that are young, less than 15 million years. You can see they're clearly clustered around this zone of Variscan foreland rocks. These Variscan foreland rocks tend to be unmetamorphosed or weakly metamorphosed compared to the hinterland rocks over here that are more durable, they're crystalline, they're higher grade metamorphic rocks. What I'm trying to explain is that these rocks are more erodible. Okay, so to summarize, there was this massive drop in base level around 13 million years ago. It increased the stream power and sent an erosive wave barreling up through the Ebro. When that wave reached the Western Pyrenees, it encountered the more erodible rocks of the Variscan foreland in a part of the Pyrenees that had undergone less exhumation. Remember this plot here? It had gone less exhumation at the end of orogenesis. And I propose that altogether, these specific factors that exist only in the Western Pyrenees can explain that 2 to 3 kilometers of post-orogenic exhumation that we see over here. So just as a final note, just to bring this back around, eroding 2 to 3 kilometers of rock from the Western axial zone would have resulted in about a 500 meter reduction in topography. That's just a simple isostatic calculation. It depends on the densities. So even considering the additional rebound associated with the excavation of the Ebro, this estimate is within the range of topographic decay that I calculated that has occurred since the Oligocene. So just to wrap up here, what I want to do is walk you through this proposed sort of tectonomorphic evolution that I've been building up to. I'm going to show you these suite of schematic block diagrams starting at about 40 MA. So 40 MA, and these gray boxes are going to show magnitudes of exhumation through time. So about 40 MA, the Ebro was open. There was ongoing crustal thickening and rapid exhumation in the Western Pyrenees, in the Eastern Pyrenees. However, in the west, inversion was still ongoing. There wasn't significant crustal thickening, and there was very slow exhumation. 30 MA, we saw the Ebro Basin go endorheic. We saw this propagation of deformation westward. The Eastern Pyrenees have accumulated at this point 15 kilometers of exhumation, and that uplift rate is about to drop. In the Western Pyrenees, that rock uplift rate is on the rise, but it still has only experienced a small amount of exhumation at this point. About 15 MA, this is peak conglomerate deposition in the Ebro. That's what these orange stippled areas showing, is this really thick conglomerates. Ebro is about to connect to the Mediterranean, which is going to launch this erosive wave up. In the hinterland, we saw about 18 kilometers of exhumation has occurred now in the Eastern Pyrenees, and much more has occurred in the Western Pyrenees. We're up to about 15, but what I propose is that there's this area here that still needs to undergo an extra 2 to 3 kilometers of exhumation, where we're going to see those really young cooling ages. And that happens beginning at about 15 MA, when this Ebro Basin opens to the Mediterranean. And here we are today. The Ebro Basin and the South Pyrenean zone are excavated. We saw this rebound and this extra 2 to 3 kilometers of exhumation in the Western Pyrenees, getting us to the point where the total magnitude of exhumation along strike is equal, but has accumulated at very different rates. All right, so that's all I have for you. Just to run through my conclusions, I talked about documenting the topography of the Pyrenees through time. We saw the relief of the Pyrenees rapidly increase in the Eocene, but there's been only really slow, limited decay since the Oligocene. Total exhumation appears constant across the orogen, but occurred at different rates. And finally, the exhumation of the Pyrenees, as recorded by these low temperature thermochronometers, was influenced by pre-orogenic tectonic inheritance, Cenozoic wedge dynamics, and these post-orogenic surface processes. So with that, I'll say thank you, and I will take any questions. And I guess I'm supposed to stop sharing my screen now.
Thank you, Maggie. This is great. Very, very interesting stories. So if you guys have questions, you can type at the chat or you can unmute yourself. But let me start with the first questions by Francis Peel. He said, actually a couple of minutes ago, great talk so far, really interesting. Do you assume that TE is uniform across the whole of a plate, or does it vary with position on the plate? Either uplift, down, up dip, down dip, and laterally.
Question, Frank. Hi, Frank. So I actually tested a range of scenarios. I did do it with a spatially variable TE, where I changed it both moving away from the orogen and then sort of laterally. And to be honest, I didn't find a significant difference in the results. So I tend to go with the simplest solution, where I use a uniform TE on each plate. So I do use a different one for the two plates, but within each plate, it's the same. But I can tell you that I did do a lot of tests where I varied it spatially. And, you know, honestly, the Pyrenees are a pretty small origin. So it didn't make as much of a difference as it might have in a really big origin where you had really, really broad differences.
Yeah, I thought it might vary quite a lot with the hyperextension and become significantly weaker where you had hyperextension.
Yeah, I didn't find that to be the case, but you know, if you, it's really hard to move around here. My mouse is stuck, hold on. If you look at these results, you can see that I had a really poor fit to the data over here in this dark purple area. So really, you know, where I consider it to be a true foreland basin is really kind of cutting off here. Over here, the profile of the basin does not resemble a foreland basin at all. It's sort of flat. It's broken by these extensional normal faults. And so, you know, to be honest, I would say over here, the basin does not resemble a foreland basin. So that sort of is like answers your question, I think, whereas, yeah, where it was really widely extended, a flexural model is not the best way to deal with it. It's a good question, though.
All right, so Toby Larson asking, following up on elastic thickness, is that a transient parameters and will it be changed across strike over time? What other parameters go into the best fit calculation for elastic thickness?
Yeah, good question. So to answer the question about time, no, this is an elastic plate model. It's not viscoelastic, so there's no time parameter at all. It doesn't, you don't see relaxation of the crust. It's just elastic. So it's like you apply the load and it immediately reacts. You remove the load and it'll immediately react. In terms of what goes into that calculation, here's the equation for rigidity at least. So, you know, it's considering the physical parameters of the crust, density, Young's modulus, Poisson's ratio. But TE really, it's sort of this, you know, nebulous parameter that really is reflective of a lot of different things like rheology, temperature, crustal structure, discontinuities. So, you know, TE sort of incorporates a lot of that, but it doesn't explicitly, you know, this is not a thermomechanical model using a viscoelastic crust. So it's not really looking at those types of parameters in great detail. Does that answer your question?
Yeah, that's good. I was wondering, I guess when I, you know, thinking in the beginning of the talk with the TE and the crustal deformation, but then with the change in exhumation across strike, that's where I was wondering, like, you know, both spatially and, you know, time-wise, does TE vary, and does that have a big effect on your resulting exhumation history?
So when I was considering the exhumation and doing that modeling, I just use a single value of TE actually in the thermo-kinematic model, which I use 20, which I think is a pretty good average between the two. And so no, you know, in terms of what is the model actually looking at, it's not looking at variations in TE. I didn't incorporate that. But I think your question gets to something else, which I think is important to talk about, which is that, you know, I see this really, really distinctive along strike trend in exhumation. But what I need to acknowledge is that my topographic analysis is really a first order topography. It's not really considering along strike variations in topography. And now I did look along strike and there wasn't, you know, great evidence to sort of say, wow, you know, at the end of the Eocene, the Western Pyrenees was, you know, much lower topography. So, you know, the topography is really a first order investigation. It's looking at how the whole orogen evolved. And yeah, looking at the exhumation, I was looking at a lot more detail. I'm still not sure that totally answered your question.
No, that's great. Yeah, and it was a really nice talk, Maggie. Thanks.
Thanks.
All right, Maggie, so there are like 8 more questions. I'm gonna read that, and then if you want to discuss with Maggie, you can unmute yourself. So Jingyu Zhang asking, so first he make a comment, great talk, really interesting. He has 2 questions. First one, how was misfit function in the first study are defined? Second question, in P-cube, is the landscape modeling mostly governed by stream power law? Is that possible to consider climate precipitation in P-cube? One comment he made, it would be nice to forward model the landscape in Fastscape or Badlands to test the last hypothesis about the 2 to 3 kilometer exhumation.
Yeah, sorry, who asked that question? I can't see the chat at all.
Okay, it's Jingyu Zhang.
All right, thanks. All really good questions. I love that you asked that. So first, you asked what the misfit was in the first round of modeling. This is root mean square error. So this is just, you know, it looks at basically the data minus the model. You square it and you sort of divide it by the number of elements and take a square root. It's a root mean square error for the first bit. The second one is, let me see if I can find that. Here we go. It's a chi-squared measurement. That's what comes out. A reduced chi-squared is what comes out of P-cube. So when you say when I show misfit here, that's a reduced reduced chi-squared measure. Second question, P-cube does not consider landscape evolution. It's a purely thermokinematic model. It just does rock advection. So there's no actual removal of material in P-cube. That being said, the final part of my project is using Fastscape. I didn't have enough time today to include that in this talk, but I am doing a bunch of Fastscape modeling, and I'm working on that paper right now. So you'll have to stay tuned.
All right, thank you, Maggie. Jake Koval made a comment, Maggie, that was outstanding talk. Thank you very much. Next question from Peter Ikumo. The way I understand the first part, you treat flexure as the crustal scale problem. So mental processes and mental lithosphere interactions also control the flexure?
Good question. Yeah. So, hi, Peter. Yeah, the flexural model is really only looking at, the flexural model does not in itself incorporate mantle processes. Do mantle processes influence flexure? I mean, mantle processes certainly influence vertical movements. So in that way, yes. Now I did consider, let me see if I put that in background here. No, I didn't put any background slides here. Great. But I did consider, I looked at the gravity data to try to understand, try to incorporate, for example, there's an area of the Pyrenees that people have concluded is a big mental sort of upwelling and how that might affect the results. And actually I incorporated it, but it was a very small influence on the vertical movements, on the order of about 50 meters total. And it was only over here. So to answer your question, no, I didn't really incorporate mantle processes. Yes, they matter. I did try to quantify how much they might matter here, and it was very little.
Let me follow up here. Can you hear me?
Yeah, I can hear you.
See the mass. It's really the first part is mass balancing. Really, the weight of the excess crust pushing down, right? Like your pig on the trampoline. But doesn't the mass of the lithospheric plate also matter here? I mean, it's kind of a subduction zone type of structure. So the mass of the plate, not just the mass of the excess topography, would control the deflection, right? And variations in the mass.
So, okay, let me try to answer that. So first of all, when we do this modeling, we model it as basically, it's just an elastic plate. So right. You don't actually consider the mass of the lithosphere when you do that. You consider everything that's the load. So, the weight of the sediment is in there and the crustal root is in there, but not the weight of the plate. But if, maybe this is what you're wondering, as you pointed out, the Pyrenees are a convergent margin. And so, you have this sort of underthrusting plate scenario. So one of my co-authors actually does sort of the more thermomechanical modeling of things. And he did a test to determine what kind of influence this, what we would call slab pull, would have. And in this setting, it was negligible. It didn't matter. I also, in my modeling for the flexure, I incorporated intraplate forces, so where I could kind of, again, sort of simulate either a slab pull type of thing. Again, very, very small. So we concluded that in the Pyrenees, the forces that are being put on the edges of the plates are not making a huge effect. And to be honest, that's not a surprise because there wasn't really much subduction here. It was a hyperextended margin. The only place where oceanic crust was being produced was in the far western part. And so there really wasn't a huge slab here beneath the Pyrenees. So we find it didn't make a difference, and that sort of fits what we know about the geology.
All right, thanks.
Sure.
All right, there are 5 more questions, and if you guys need to leave, you can leave first, but I'm gonna finish these 5 questions.
Okay.
David Lorick want to ask, did you look at a broken plate scenario? And David, if you want to unmute yourself to discuss with Maggie, please welcome.
I did. I did consider a broken plate scenario and a continuous plate scenario. I didn't include the results here. I just went with the continuous plate. But what I can tell you about it is that looking at the broken plate, I get overall similar trends, exact same trends, but the value that I get for TE, so I'll go to this right here. So here, this is the continuous plate. So the actual values I get for TE are far higher when I do this with a broken plate. And now that's no surprise because I guess you guys can't see me, or maybe you can, I can't see myself. But when you have a broken plate like this, you're actually able to put more force on the edge of that plate. And when you bend it more, you're really getting an effectively different value of elastic thickness. So basically to get the same flexural response in a continuous plate versus a broken plate, you end up having a much higher value for TE. I think I wish I'd put these slides in background. I forgot, but anyway, yeah, I did look at it, but I would argue that a continuous plate in a setting like this is sort of more reasonable because a broken plate assumes that there's really no interaction between the two plates, when in fact we know that these are highly viscously coupled. There's an incredible amount of friction going on here, and so arguing that one is being able to act without the other is, to me, I always thought it a hard thing to defend. But I did look at it.
Okay, thanks.
Yeah, Maggie, we can actually see you.
Oh, okay. Hi.
Susan, from Susan Hiroka, what controls the distribution of sediment shed to the north and south? Is it 50-50? Seems in some settings it is asymmetric.
What controls the sediment dispersing, sort of between the north and the south? Is that the question?
Yes.
So that was not really something I explicitly looked at in this study. But, generally speaking, what's controlling what's dispersing to the north and south is going to have a lot to do with, well, what's the accommodation like on the north and south, how these wedge dynamics are evolving. So if you look at, I'm sorry, my mouse is being a little funny here. If you look at this cross section, as that wedge is evolving, you might have more sediment ending up being eroded to the north versus the south. We know that drainage divide migrates through time. So there's a whole lot of factors that will control whether sediment is going to the north and the south. I'm not sure I did a good job answering that. I didn't really explicitly look at sediment dispersal in this study.
Thanks, that's the answer.
Okay.
Thank you. So next question, Mike Hudak, he made a comment, first great talk. He asked, casted uplift varying along the strike and cross dip, both are likely relevant. Is there any way to look at the fit varying both at the same time?
Yeah, no, yeah, you're right. So the comment is that, I conclude that there's this really dominant east to west propagation. A lot of studies have found, particularly in this region of the Central Pyrenees, where the wedge is sort of most well developed, that there has also been a north to south trend. I find that as well. As I mentioned, I looked at one of the models I considered was sort of the structurally controlled. Man, my mouse is bouncing all over the place right now. Here we go. Get to that slide. Okay, so I looked at this type of trend as well, and the only place I found it being significant was in this area right here, this sort of East Central Pyrenees. So to get your question, is there a way to consider both at once? Yeah, there is. But I'm not, I'm not doing that right now because mostly what I wanted to do here was sort of compare these two different models. It would involve a little bit more complication in the model, and when you start making these models overly complicated, it gets a little bit difficult to deal with. For example, because of where the data is actually found. So when I start breaking these into smaller and smaller bits and trying to model different parts, you get areas that have no data, areas that have a lot of data. So that becomes becomes a lot more relevant. But yeah, the answer is yeah. I mean, I know it's important, particularly in this area right here of the East Central Pyrenees. So if I were trying to do a really accurate model, which is something that my colleague is doing, that would involve incorporating both a west to east trend and these wedge dynamics that we know occur with the north to south movement. That answers your question, Mike?
Yeah, Mike, do you want to unmute yourself?
Yeah, that answered my question. Thanks, Maggie.
Thanks, Mike.
Next question from our energy director, Mark Schuster. Nice talk. Any thoughts in variation of paleoclimatic and paleorelief effects on exhumation rates throughout the Cenozoic?
Yeah, well, I'll comment on paleoclimate. So there is somewhat of a precipitation gradient. We know that the French side, for example, gets a lot more rain currently than the southern side. If you've ever been to the Pyrenees, you can see that clear as day. The south is lovely and dry, and the rocks are clearly exposed, and the north looks like the Appalachians. It's all green. So I know other people have really looked at that in more detail, and basically what people have determined is that even though we see somewhat of a precipitation gradient today, this sort of gets back to the Pyrenees being a relatively small origin. These are not the Andes, they're not the Himalayas. So we don't see such just very dramatic climatic effects in terms of erosion in the north versus the south. So we tend to think it's probably not a huge factor. That being said, it's never been explicitly studied trying to understand, for example, how modern erosion rates in the north vary compared to the south. That would be something that could be done to really get to the root of that, but no one's done it yet. The second question was how paleorelief might affect the exhumation. I think that was the question.
Yes.
So I think if I understand that right, maybe what you're wondering is, was there any relief that existed sort of at the beginning of the Pyrenean period that might affect how we're observing the exhumation today? I might be misinterpreting that. So I would say, there was almost definitely some kind of relief at the end of the hyperextension. But we also know that a lot of it involved carbonate platforms. We have a pretty good sort of paleobathymetry marker in the Mesozoic prior to all of this beginning. I didn't explicitly incorporate those types of sort of pre-orogenic relief that might have existed. That would have been good to do, also kind of difficult. It probably had an effect, but also when you're considering particularly these really low temperature thermochronometers, and sort of through this whole orogenic period where we know 10 to 18 kilometers of exhumation occurred, probably the signal that we're seeing at this point, for example, in some of these lower ones, probably that signal at this point has been sort of reset. So we're not I would doubt that these really low temperature ones are reflective of pre-orogenic topography. Now, the zircon fission track and helium, that might be more so. It's a good question. I don't have a very good answer to it.
Yeah, thanks, Maggie. Appreciate the answer. Great talk.
For our last question, Gil asks, would your model be at all sensitive to whether the foreland is underfilled or filled completely? In the Eocene, there was the turbidite basin in the west, fluvial in the east of the southern Pyrenean foreland.
Mhm. Yeah, the answer is yes. It would be affected by that. Let me get to this slide here. So I did try to incorporate that. So as I said, I did sort of reconstruction and backstripping at all these different stages. And I attempted to account for that type of paleobathymetry. So as you mentioned, we know that there was a turbidite succession early on in the development, what they call a flysch basin. And so I did try to take into account that at that point, it would have been an underfilled basin. It wasn't totally filled up to the top with sediment. It would have been partially water. So, I mean, what that really gets down to is what is the density and the thickness of the sediments that are providing a load there. So I did try to incorporate for that, and I used a depth-dependent density. And I, you know, when I knew it was underfilled, I tried to reconstruct it as underfilled. You know, there's a little bit of guesswork that goes on there, as you know. You know, how underfilled was it? How deep was that basin? Don't know exactly, but I did try to make a guess at it, an educated guess. And yes, it does matter.
Thank you.
All right, cool. More comments just about, thank you for such an interesting talk. So we are at 10:07 right now, so it's a little bit delayed, but there are a lot of great questions, and this is a really interesting talk. Thank you, Maggie, and thank you for your time, and welcome everyone to next week's seminar. Thank you.
All right, yeah, thanks again for having me, and thanks everyone for the good questions. If you have any other ones, you're welcome to send me an email. You can find that email online and let me know. But yeah, thanks again, everybody. It was fun.
Thank you, Maggie. Thank you.
So long. Yeah.